We're happy to have today Sasha Efimov from the Steklov Institute in Moscow. The title is on the screen. Lina will send slides in the chat. Actually, I think he did it. And if you'd like to ask a question, just unmute yourself. So kind of, we are not very formal here. All right, Sasha, please.
Okay, thank you very much. So I will talk about nuclear modules over proper DG algebras. This is basically my attempt to understand the recent theory of condensed mathematics, and in particular nuclear modules over analytic rings as defined by Clausen and Scholze. I will start by recalling some. I will be interested in the commutative algebraic geometry. I will be interested mostly just in formal schemes, and then I will explain what it means in terms of non-commutative proper DG algebras. So, but I will start by recalling some results on perfect complexes, on usual Nasserian formal schemes. Their relation, how they're related with pseudo-perfect models over proper DG algebras. Then I will recall dualizable presentable DG categories and how they naturally arise in different contexts. Then I will sketch the definition of solid models. This is part of condensed mathematics, this due to Clausen and Scholze. And I will again specialize just to the case of basically affine Nasserian formal schemes, and then recall the definition of nuclear modules, which form a full subcategory of solid modules, which turns out quite surprisingly for me to be a dualizable presentable. And then I will explain that certain enlargement of their category, some unbounded version of nuclear models, it naturally makes sense just for arbitrary proper DG algebra over commutative ring. And I will give a general definition in this case of the category of nuclear models and sketch the proof of dualizability of this category. And finally, I will try to explain that this category is a special case of internal home in a certain symmetric monoidal category. And this is basically, to people who are familiar with dualizable categories, what you need to consider is basically dualizable categories and strongly continuous functors between them. Functors with continuous right adjoint. So somehow this, I guess, wasn't considered before, and it is very closely related with this notion of nuclearity. Okay, so I will. Well, I assume that people are somehow familiar with the DG categories because it's not really preliminaries on DG categories. It's basically mostly fixing some notation. So for a small DG category, I will denote by D of A the derived category of right modules over A. And I will denote by mod A the correct DG category of A modules. For example, you can take semi-free A modules or homotopically projective A modules. Inside this category, we have perfect complexes, which are the same as compact objects. And we have pseudo-perfect complexes, which is basically A modules which are perfect over the base ring. The tensor product of DG categories and DG algebras will always be derived over the base ring. And for small DG categories, when I write functors between A and B, I mean again the correct DG category of functors, which is the internal home in the symmetric monoidal homotopy category of DG categories, where you invert quasi-equivalences. Now the basic definitions, which is due to Kontsevich, so DG algebra is proper if it is perfect as a complex of K modules, and the GeoGebra is smooth if the diagonal bimodal is perfect. So you can think of the condition that A has a finite resolution by finitely generated projective bimodals. So almost trivial observation that for a proper GeoGebra, we have inclusion, perfect complexes are contained in pseudo-perfect, and for smooth GeoGebra, we have reverse inclusion, pseudo-perfect are contained in perfect. Now, another notion which will be important for us is certain weakening of.
I'm sorry. What is the meaning of the word pseudo-perfect?
It was on the previous page. It means perfect over the base ring.
Mm-hmm.
I mean, it's terminology due to Toyen. I don't know if it's optimal.
It's okay, but just
just perfect over the base ring. And you can think of them as functors from like A opposite to perfect complexes over K. Okay. The notion of homological epimorphism is a certain weakening of localization. It's basically the condition that B tensor B over A is isomorphic to B, I mean quasi-isomorphic. It means that the extension of scalars from A to B is localization functors, which is the same as requiring that the restriction of scalars is fully faithful. And of course, probably most such homological epimorphisms which you encounter are given by Drinfeld quotients of DG categories. So if you take perfect complexes and mod out by some subcategory, then you of course get this homological epimorphism. But there are much more homological epimorphisms than just quotients by subcategories generated by complex objects. And this is actually equivalent. It is not hard to show that it's equivalent to F being a homotopy epimorphism, which means that basically homotopy coproduct. I mean push out B and itself under A is the same as B. The notion of homological epimorphism also makes sense just in a similar way for a functor between small DG categories. It is equivalent to, again, to the property of being homotopy epimorphism in the Morita model structure, where you invert Morita equivalences. We will need an algebraic version of Kalkin algebras and more precisely of Kalkin categories. This is defined for any small DG category A. It's basically you take the DG quotient of A modules by perfect modules, and here I'm taking Karuba completion. It's not really important at this point, but let's make this convention. These are the basic notions which we will need, and I will often take DG algebras instead of DG categories because, I mean, for most people, I guess it's easier to think about DG algebras. And I will use notation like we take representations of A in some DG category T, which is the same as functors from A to T, if you consider A as a category with one object. And also I will denote by DG cut triangulated the infinity category of retriangulated Karuba complete small DG categories. Now let's consider affine Nasserian formal schemes. And so just take a commutative Nasserian ring and an ideal I in R. So we have a affine scheme and we have a closed subset defined by this ideal. So the perfect complexes on this formal scheme, it is basically perfect complexes over the completion. Well, it is also the same as the homotopy limit of perfect complexes over R mod I to the N. So I want to interpret this category as pseudo-perfect modules over some proper DG algebra. So for that, take some generator. For example, you can take Koszul complex, for some system of equations defining this subset, and take the DG ring of endomorphism of this perfect complexes which is a proper DG algebra over R. So here our base ring is R. So
no, I think you assume that this Z is zero-dimensional.
No, it doesn't matter. No, Z is just any subset. I mean, our base ring will be R.
Okay.
Yes. So we have an equivalence. Derived category of A is the same as quasi-coherent derived category of X supported on Z. So basically, proposition I attributed to myself basically because I didn't see it anywhere, but maybe it was known to people. That perfect complexes over this completion is identified with pseudo-perfect complexes over A. Again, where the base commutative ring is R. So the equivalence is given by F goes to R home from E to F. So here we identify the perfect complexes supported on Z with perfect complexes over the completion with torsion homology. And the inverse equivalence, it sends a pseudo-perfect A-module corresponding to a complex. I'm sorry, it's not A, it's R here. So we have a pseudo-perfect A-module which corresponds to a complex of R modules with E-torsion cohomology. Then we take the inverse limit of M tensor R mod I to the N. And this inverse limit will actually be a perfect module over the completion. And these are inverse equivalences.
Sasha, probably this equivalence is well known in some particular cases. Could you give us some example? If this proposition is important for you, it would be nice to give an example.
Yes, I will give an example.
Is it something like Koszul duality or what?
Yes, it's exactly a kind of Koszul duality. I will give an example on the next page.
Like like 0 on the fine line.
Yes, I will give an example of zero-dimensional scheme on the next page.
Then you get probably Grassmann algebra or something like that.
Yeah, okay. Jan, exactly. That's what will appear.
Okay, sorry.
Almost immediately. I just.
So a general remark is that speed is a little bit too high.
I'm sorry.
Yeah, but, especially for graduate students.
I don't know whether we have strict time constraints or not so strict.
It's semi-strict. It's semi-strict. You see, you have it's semi-strict, which means Sasha has 90 minutes, and then there will be Q&A question, and then it can continue. Volodya, it's as strict as your seminar. So, like the talk, then sort of a break. People can leave.
Okay, I can actually slow down, but
so nobody will tell us that neither President Putin or President Biden will tell us that we have to stop at some point.
Certainly they will not.
Yeah, they will not. Yeah.
Good. So maybe then it would be better to speak a little bit slower.
And also, Sasha, it might be a good idea to stop and take questions because, you know, otherwise people can, you know.
Yeah, okay, it makes sense. Okay, I will.
All right, go.
I will try to slow down. Okay.
So my question was about a baby example of this, and you said that it's on the next slide.
It's on the next slide, yeah. But I mean, basically, the baby example is, of course, given by a fine line and a point. And yeah, as Jan mentioned, you get so this DG ring. Yeah, okay, let's wait for the next slide. It will be a little bit different framework, but still the same example. Okay, so a global version of the statement is the following. So we take now some smooth separated scheme of finite type over a Noetherian ring K, and take closed subscheme, which is a proper scheme over K. So in the previous example, X was actually the spectrum of K, and we just had a closed subset. So again, we take some generator of perfect complexes with supported on Z, on X, and take the proper take the endomorphism DG algebra, which is a proper DG algebra over K. Now we have a more general equivalence. So we take perfect complexes on this formal scheme, just completion of X at Z, and they're again equivalent to pseudo-perfect modules over A. And this is less well known, and the statement is more complicated, but still it's not very hard to establish. And a standard baby example, which I formulate in this slightly more general context. So let K be just a field, and we take a fine space, and Z is just the origin. And if we can take this generator to be the skyscraper Schiff at 0, and then the DG algebra, the endomorphic DG algebra will be just exterior algebra in n generators, just exterior algebra of the tangent space 0. And you compute. So first, the category of pseudo-perfect modules, it is generated by the one-dimensional trivial module K. And if you compute its endomorphism, you get exactly a power series in x1, etc., xn. But this situation is actually much simpler than the general one. In general, the DG category of perfect complexes on this formal scheme, it is not generated by a single object. And in fact, sometimes it might happen that the minimal cardinality of the generated set, it might be just the cardinality of all sequences of elements of K. So in particular, if K is finite or countable, then you might need a continuum of objects to generate the category. For example, this happens for the formal neighborhood of P1 in P2. Just take a line in projective plane, and if you take the formal neighborhood, then you just have too many line bundles, and you can figure out that it's very hard to generate the category using some small collection of objects. It's only small in the set that it forms a set, not a class. Okay. So are there any questions at this point?
I have the following question. It seems to me that I have some problems with sound. It seems that I don't hear all the words the speaker is saying. And the question is whether it's only my problem related to my internet connection, or is it a problem of the whole audience?
I don't have a problem.
No, I don't have this problem.
Okay, so that's my problem.
Okay, but anyway, if there's a problem with sound, yes, then still, I mean, if you don't hear something, then all questions are welcome. So I will clarify and repeat. Okay.
Actually, Sasha, maybe I just want to understand more examples with P1 and P2, yeah? Which you
yes.
mentioned. Yeah. Now, if consider category of perfect complexes on X supported on Z, not on Z hat, but on Z.
Yeah, then it's of course generated by a single object. Yeah.
Yeah, but yeah, okay. So it has nothing to do.
Yeah. Well, I mean, of course, always this category contains this subcategory of torsion perfect complexes.
Yeah.
And the problem, I mean, for example, you can mod out by this subcategory, so you consider punctured formal scheme, and still you might need a huge collection of objects to generate the category.
Ah, yeah, I see.
Yeah.
Just a moment. So as far as I understand, any coherent sheaf on P2 gives you an object. No, but this is not. This doesn't. This subcategory. Is it obvious that it has so many objects?
Well, it's not immediately obvious, but yeah, it's non-trivial statement actually.
Okay.
I mean, I have,
but this example
so,
with formal neighborhood of P1, I mean, is it obvious in this case because you have line bundles of any degree and so on?
No, the problem is not degree. The problem is there's huge, I mean, continuous.
Sasha, yeah, but can we see this category something like analogous to suppose we consider like coherent sheaves on affine plane or whatever,
Yeah.
dimensional with one-dimensional support? Yeah, then it will have infinitely many generating. Is it something like this?
Well, it's somehow related, but no, but not exactly. I mean, let me give just some small example. Yeah, unfortunately, it's not written here. So again, for this one in P2 or more generally, you can ask a question. So take some perfect complexes on this formal scheme, and you can ask, is it generated by the image of perfect complexes on X? And it turns out that if you consider germs of some curve transversal to Z, well, let's say in this special case, P1 and P2, then this condition is closely related with the condition. It's actually equivalent to the condition that the corresponding power series is algebraic. So you can express algebraicity of power series in terms of this condition on being generated by the perfect complexes on X. This is non-trivial statement. It's actually some careful analysis of the Drinfeld quotient in the situation. But I mean, it's a slightly different topic. I mean, probably.
Just a moment. I still want to understand something about the situation. So
Yeah.
suppose instead of perfect complexes, I asked myself how many vector bundles are there on this formal scheme. For instance, how many line bundles? In the case of line bundles, they are parameterized by H1 with coefficients at O star, and then you have a filtration on O star, which gives you some idea about the size. And
Yes.
if I continue this way of reasoning, will I see that there are many so many vector bundles on this formal scheme that it's very unlikely that category of perfect complex is, let's say, finitely generated.
Well, it's not immediate to show that some line bundle or even that there exists a line bundle, for example, that is not generated. I mean, to show that it's not generated by the image of perfect complexes on X, you need some additional ideas. I mean,
yeah, of course you cannot, but at least is it true that there are much more, many more vector bundles on this formal scheme than those obtained by, as restrictions of.
Yeah, that's true for sure, but that's true, of course, yeah. But asking whether a vector bundle is generated using
yeah, of course, after this observation, you have something to prove. But this is a way to make oneself believe that there are many.
Exactly, yes. Yeah, that's right. Okay, so this is some brief discussion about perfect complexes on formal schemes and pseudo-perfect modules over DG algebras. And so basically, my idea of understanding what Clausen and Scholze did, I mean the category which they constructed, so I wanted to understand what it is and figure out does it make sense for GG algebras, and this is what I'm going to basically explain, because for this associative GG algebras you have much less freedom. So for example, you don't have symmetric monoidal structure and so on, if this is just some abstract GG algebra. So I just wanted to make sense. I wanted to figure out if this construction has some general non-commutative categorical nature, and it turns out that it does. So that's actually the main topic of the talk. Okay, so here's just some intuition which turns out to be useful here. So for an abstract proper GG algebra A of a commutative ring, one can think of perfect complexes over A as perfect complexes with torsion homology on some smooth non-commutative formal scheme over K with a proper subscheme of definition. So this is just a way of thinking about it. And continuing this, pseudo-perfect models can be thought of as perfect complexes on this non-commutative formal scheme. Now, if you continue, you can consider what Orlov calls the category of singularities, which is the quotient of pseudo-perfect complexes modulo perfect complexes. Well, let's say Karoubi completion of this. And this can be thought of as the category of perfect complexes on the punctured formal scheme. For example, considered as an adic space in the terminology of, I mean, in the framework of Huber theory. So in terms of Kalkin categories, we have the following observations, which for now may seem to be totally unnecessary, but it will turn out that they're actually crucial observations and quite tautological. So first, pseudo-perfect models over A. This is the same as the kernel of the functor from A modules to representations of A opposite in the Kalkin category. So A modules, this is representation of A opposite in K modules, and so we have a natural functor. And tautologically, a model is pseudo-perfect is exactly if it is in the kernel of this functor. And similarly, the category of singularities is the kernel of the functor from the Kalkin category of A to representations of A opposite in the Kalkin category of the
Is it obvious that it's a tautological observation?
Well, yes, because an object is in the kernel exactly when the underlying K module goes to 0. And
this is a quotient. Okay.
Yeah. Okay. Yeah. So this is this is a quotient by perfect complexes. So this is indeed tautology, but it turns out that this is exactly how you should think about this category, and we will encounter this later. So are there any other questions at this point?
Sorry, Sasha, a quick question.
Yes.
Why, I mean, smooth and proper DG algebra corresponds just to a non-commutative scheme. Why a proper algebra corresponds to a smooth formal scheme?
No, but I mean, smooth and proper is like the case when x equals z.
Yeah.
Yes. So I mean,
this is I want to understand why are we thinking about the proper DG algebra as the smooth and C formal scheme. I mean, where does formality comes from? And second question is, what is torsion cohomology? Just very quickly.
Yeah.
No, but as I explained, this pseudo-perfect models, they give exactly, I mean, this is somehow, they already contain the information about the completion. So I mean, you can think of this as completion.
Yeah. Also, Sasha, there is also kind of another. If you have this proper D algebra, you can think it's like finitely many non-commutative variables, form power series ring, and derivation. Yeah, that also can trade.
Yeah, okay.
Kind of bar construction. Yeah.
Yeah, I see. Yeah, but I think this picture is more appropriate here. I mean,
yeah. It's more or less the same. I think it's actually more or less the same. You can replace your commutative situation by formal affine space and point in it.
Yeah, probably. Yeah, probably there's a way. Yeah, just a way to translate it. Yeah, especially if you think of the pseudo-perfect models as infinity models, then probably you can. Yeah, in your picture this is visible. Yeah, I see. Okay.
And what was torsion cohomology? Just torsion in what sense?
Once again, torsion Timothy, once again, what is the question?
I will ask, you are talking about perfect complexes with torsion cohomology. So in what sense torsion cohomology? Sorry.
Annihilated, I mean, the cohomology is annihilated by some power of the ideal of definition.
Thank you.
Sasha?
Yes?
I have a question which I'm not sure that it's possible to answer, but still, I hope. Is there a non-technical way of explaining your goal? So who is your enemy and what are you struggling with, and whether you achieved success or whether you achieved only partial success? Can you say something maybe not quite precise, but easy to understand?
Well, I had for quite some time I had just a general idea that when you encounter such categories like pseudo-perfect models, which are very poorly behaved in terms of K-theory, in terms of, I don't know, Hochschild homology, in terms of localizing invariants, then the correct picture should be that this category is compact objects inside some very nice, I mean, much more reasonable dualizable category. And so I had this point of view already for some time, like for 5 or 6 years. And somehow I was thinking about constructing such dualizable categories at least in this framework of formal schemes. And so basically now I finally understand what the answer is.
And before explaining what the answer is, was your so you started by saying that you had some vague hope.
Yeah.
What is the result? That the hope turned out to be true,
yes.
Or that it had to be modified?
No, it's true.
It's
but
true.
Still, the answer is not very easy to comprehend.
But the picture is true, and it makes happy, and makes you happy.
At least partially, yes.
And then again, you said that this. Can you say again what is the simplest case? You said in abstract terms that you were you were thinking essentially about the nature of DG categories of certain type, and you described this type of DG categories in some abstract terms that I was unable to grasp. But can you give a particular example of the geometric or some other type of situation?
Yeah, I mean, my hope, which is still a hope, is that in some situations when you have, for example, complex manifold or a rigid analytic space, which is not necessarily algebraic,
yeah.
Then there should be still so the coherent sheaves on this derived category of coherent sheaves or perfect complexes on this manifold, they don't reflect really much information about the manifold. And I still think that there should be a reasonable dualizable category of the correct version of specific initiatives, which allows
no, understand. This is what always puzzled me, and probably many people were puzzled how to define a good theory of sheaves on, let's say, on complex manifolds, maybe proper complex manifolds, which are not algebraic. And then it's not clear what to do. But I think now, did you achieve this particular goal? Probably no.
No, in the complex setting, no.
What about the non-Archimedean setting?
In the non-Archimedean setting, it's not completely clear to me, because this answer, it gives something for non-algebraic rigid analytic varieties, for example, for proper non-algebraic rigid analytic varieties. But it's not really, I don't have a clear understanding of what's going on with K-theory, which you can define for dualizable categories and homology and so on. So my idea was to understand, to approach this non-algebraic spaces.
Yeah. So the dream, the original dream was probably about complex.
Sorry, maybe I interrupt. Yeah, it's Maxim. I think actually with Tony Pantev and Ludmil, we had some idea how to define on complex varieties as large categories of quasi-coherent sheaves, whatever it means, which will be dualizable, and like if you have
I guess it's not dualizable
transform for complex store, it will be equivalence of such guys.
No, but Maxim, I think it's not dualizable in the usual algebraic sense. I mean, if you don't consider nuclear Fréchet or something.
So just a moment, Sasha. As far as I understand, the original dream was about complex analytic varieties. This is too complicated. The next dream was about non-Archimedean, let's say, proper varieties. And this dream also hasn't been achieved, but still you achieved something. So what was, can you somewhat informally describe what you really achieved?
Well, the definition of the category in this geometric setup, it was given not by me, but by Clausen and Scholze in this formalism of condensed mathematics. So what I was trying to do is to understand this construction and to understand it categorically and probably simplify it. So, I mean, to figure out what it means and
okay, so your goal was to understand and to simplify the Clausen-Scholze construction.
Yes. I mean, for now.
Now understand.
Yeah.
Sorry.
Yeah.
Sasha, I don't know. I think I said something, but probably you didn't listen. No, I said that with Tony Pantev, I think we have idea how to define right category for quasi-coherent sheaves.
No.
Nuclear spaces.
I thought this, but
nuclear spaces. Yeah.
I thought that this category, which you consider, it's not. I mean, is it dualizable in the usual algebraic sense? Just
I think. Yeah, in fact, I don't know.
That's the problem, because I think you have this condition like homological epimorphism, but not in the usual linear algebra.
Yeah, it's in nuclear spaces algebra.
Yeah, and that's so that's quite different.
Yeah, and also for just Svoloda ask you the simplest example, like exterior algebra, like point in a fine space. This example is quite complicated, and I will come to that later. I mean, the problem is that even in the seemingly trivial cases, this category is complicated, and I will probably explain why. Yeah, and also the last question: do I understand what you will construct is this like pseudo-perfect modules of algebra will be perfect complexes in some dualizable category? Yeah.
You mean compact objects in some dualizable category?
Yeah. Okay.
Yes,
Okay.
exactly. Yes.
Okay.
Yeah. So now, yeah, probably what I already partially mentioned for a formal scheme, this category of perfect complexes is poorly behaved with respect to localizing invariants, such as K-theory, and the main reason is probably that just the restriction to an open subset is not a categorical localization. So, for example, if you take polynomials in X and take power series in Y, and then invert X, it's not the same thing as to take power series in Y with coefficients in Laurent polynomials in X. And if you want to, so from the point of view of categorical localization, you of course want the left-hand side, but in practice, what you get in the case of formal schemes, you need to localize and complete, and this is quite different. So you still have the Zariski descent for this categories, but you don't have, for example, for K-theory, you don't have the Zariski descent. Similarly, the DG categories of pseudo-perfect models of proper DG algebras, they also behave poorly from the point of view of localizing invariants for similar reasons. However, if you consider Hochschild homology, which is of course not a localizing invariant, but still an invariant, then it's not hard to show that its Hochschild homology is the same as Hochschild homology of A. So, which is
what generality? Proper over a field? Or?
No. The point is, you can take any DG algebra, and you take any small category which is contained in A-modules and which contains perfect complexes.
Okay.
This is what some people call renormalization, and in this case, you have isomorphism in Hochschild homology.
Actually, I have a question. This equivalence of Hochschild homology appears in very general situation when I consider like centralizers of centralizers for centralizer. Yeah.
Yeah, but here, the point is that this category might be huge, as I mentioned.
Yes. It's even not algebra. Yeah, I see.
Yeah. Still, Hochschild homology is the same, which is not immediately obvious, but which can be proved quite formally.
Will we have a break at some point?
Okay.
Question to organizers?
Well, originally the idea was kind of 90 minutes, but we can make a break for 5 minutes now, because I consider this question as a signal that some people may be tired. Let's make 5 minutes break. Sash, don't you mind? And then you
yeah, that's fine. Yeah.
Okay, then 5 minutes break, and yeah.